Hi guys, we are going to finish question 3 of the 2018 2.6 examination today. Like always, subscribe if you haven't. If you're new to the channel, hit the like button and share the channel with your friends to help them, with some last minute revision before the examination. So let's get started with question 3 in this video. So the first one, the idea of amphiproduct species, because it can act both as an acid, it can accept or donate a proton, so that means acting as an acid or base. Make sure you remember this definition, because sometimes it may go, what is a word that describes something that can act as an acid or base? Amphiproduct is the one that you're going to go. Okay, but this is the part where you need to apply the definition of acid. So acid, what an acid and base does. So an acid donates the H, whereas a base accepts the H. Okay, so when HSO4 minus behaves like an acid, it's going to lose the H plus ions. So it's going to be SO4 2 minus because you lost a plus. So it's going to be 2 minus altogether. And where did the plus go? The plus went to the H2O. That's why you have H3O plus. They're both aqueous because they are both ions. In this case, the HSO4 minus becomes H2SO4 because, oops, that's AQ. God, don't you love it when you make a stupid mistake? That's AQ, and then that's OH minus. Okay, so just understand what an acid and base does, and you should be okay here. And let's look over here, the pH of showing below. Okay, so we got the pH here, and we got the conductivity of electricity. So explain using the difference in pH and conductivity, use relevant equations. So we can scroll down a little bit. So we know KOH must be a strong base because it has a really high pH and it's a really good conductor. So what that means, if it's a strong base, it will completely dissociate. And when it completely dissociate into many ions. So what are the ions? The potassium ions, and then the OH ions, OH hydroxide ions. Okay, so the ions that we are looking for is this guy and this guy. Because it's a complete dissociation, you only have a single error. And that means, if we look at the pH, what does the pH depends on? pH is actually, let's do that at the end once we've done all two. Once we've done both of them. NH3 is a weak base. It partially dissociates. What it means is that if you put in water, it won't completely dissolve. So that means your NH3, when it partially dissociates with water, remember this is a base, it's going to accept another proton from the H2O, so it'll be NH4 plus OH minus. Now, because this is an equilibrium, you only have a very small amount of hydroxide, actually very small concentration of OH minus. Okay, so what does the pH depends on? pH depends on the concentration of H3O plus. Okay, so obviously the more OH minus ions you have, you did this in year 11, the higher the pH. Okay, so that's why the higher the pH. That's why the pH is higher for the potassium hydroxide compared to the ammonia, because there is more OH minus ions as a result of dissociation. Okay, now conductivity. Conductivity depends on the free moving ions. So when you have so many free moving ions in potassium and hydroxide ions, then it's obviously a better conductor, whereas your weak base, ammonia, only partially dissociate, so you simply don't make as many ions. Okay, so let's look over here. Strong base completely dissociate, here's the equation. Weak base partially dissociate, here's the equilibrium. pH depends on the H3O plus ions, because you got more OH minus, pH is higher because the NH3 has less OH minus ions because it is a partial dissociation. The pH is smaller. And conductivity depends on the presence of, I'll actually add something here, free moving ions, just for good habits. And then the KOH solution has more ions because that's a K plus and OH minus, and so it is a better conductor. But why does it do that? Because it was completely dissociated. Okay, moving on to the part C. So this is below shows the pH of solution of ethanolic acid, which is right here. And just remember, any organic acids, so like anything oic acids, they are weak acids. Okay, nitric acid, hydrochloric acid, sulfuric acid, those are strong acids, so they have been given the concentration of 0.2 moles per liter. Did they make a typo in this exam? Or they didn't, because I thought this was that. All right, never mind. So they gave you the concentration. So all the concentration of 0.2 moles per liter, and they just gave you the pH. Use the pH values to analyze the strength of the acid by calculating the concentration of the H3O plus ion. So they actually want you to calculate. Ooh, part of this hurts me because it's not technically correct to use this particular method to calculate the pH of the to calculate the ethanolic acid ion. You will learn that year 13, but let's just go with it anyway. Okay, so if we were doing the nitric acid, it will be 10 to the power of negative pH, so it will be 10 to the power of negative 0.7, and then you should get 0.2 moles per liter. And if you look at that 0.2 mole per liter here, and if you look at that 0.2 mole per liter here, what does that suggest? So the two concentrations are the same, so same concentration. So that suggests complete dissociation. That means there's only one possibility for this to happen. That means HNO3 dissociated in water, and then actually let's add the H2O in just to show that. Oops, not the highlighter. Plus H2O, H3O plus, and NO3 minus. So this is a complete dissociation, because what happens? What do we know? We know the concentration of HNO3 is 0.2 moles per liter, and if we calculated the H3O plus is 0.2 mole per liter, because it's a 1-to-1 mole ratio that suggests that this is a complete dissociation. Okay, so yeah, that's how we can figure it out. The next one, if we do the ethanolic acid, CH3COOH equals 10 again. Oops, why did I do that? I was meant to do H3O plus equals 10 to the power of negative pH, which is 10 to the power of negative 2.73, and you're gonna get 0.00186 moles per liter. So this number obviously doesn't equal to 0.2 mole per liter. So this is much less. So this concentration, much lower concentration. So that means one thing, that a partial dissociation has occurred. So your CH3COOH reacting with water has partially dissociated, and then you made a very small amount of the H3O plus ions. Okay, because it's a partial dissociation, and the numbers just confirms that. Now in year 13 we don't calculate the concentration using the pH just like that. If you did that in year 13, that will be completely wrong, but then year 12, this is the only method you know. That's why we're doing it. Okay, so the first part is the same concentration, same strong acid fully dissociate, produce a lot of the hydronium ion. For the ethanolic acid, this is a weak acid, only partially dissociate, as you can see from the concentration, nowhere near the original concentration. That suggests that it's about 1%, or even less than that. It's 1%, about 1%, 2% of the original CH3COH that has dissociated into a very small amount of H3O plus ions. Okay, so that's what we can do using a bit of calculation to confirm what we know. Okay, so using the reaction, using the calculation that we done, and refer to the collision theory. So this is what this topic is actually all about. The chemical reactivity paper is supposed to, we teach you rates of reaction, so you understand that, and you have to use rates of reaction to understand equilibrium. And once you understand equilibrium, then you can understand partial dissociation, which then brings back to the ultimate question: why do strong acids do react better than weak acids? Because they would both react, but if you have HNO3, which completely dissociate, you know, this is a strong acid, and which completely dissociate, that means you have lots of H3O plus ions available at the beginning of the reaction. Okay, at the beginning of the reaction. So to go with your the rates of reaction stuff that we did, because there are lots of the H3O plus ions readily available at the beginning, this means you have more likely for Mg to collide with, and that means you have more higher, you know, more effective collision per unit time, essentially. More effective collision per unit time. So this just goes back all the way to question 1. Okay, so because you have a higher rate of reaction, because you have all of these ions that are just sitting there and they have completely dissociated and they are ready to go, they are ready to react, because they have all been produced from the dissociation. When you have the ethanolic acid ion, because you only have a partial dissociation, you only have a very, very small amount, as you can see from the calculation. In this case, this is a weak acid. You have less H3O plus ions available at the beginning, therefore the rate of reaction will be much lower. Now, if we want to elaborate a little bit more, again, whenever they say refer to the collision theory, whenever they say predict the rate of reaction, you have to talk about the effective collision per unit time, you know, compare the frequency of the collision, successful collision, But, you know, if I were to answer this question, I'll actually do a little bit more than what the marking schedule has asked me to do, you know, just to show them they understand my Le Chatelier's principle. Because if you, so this is extra stuff, okay? So this is not part of the schedule. Let's think about this. This is a partial dissociation. So out of, I normally use this example. If I had 100 of the CH3COOH at the beginning, I probably only make 1 H3O plus from the partial dissociation, 1 to 5, for example, 1 to 5%. And then I put the magnesium here, and then the H3O plus is going to react with the magnesium. And then what is going to happen to the H3O plus concentration? The concentration will go down because the hydronium ion has gone to react with the magnesium. Yeah, makes sense. The Chatelier principle states that because we lost the concentration of H3O plus, what does the system do? It's going to favor the right hand side and make more H3O plus ions. So over time, eventually you will have the same amount of products being produced using HNO3 and ethanolic acid, because if they have the same reaction, same temperature, if everything else, not same temperature, same reaction, amount of reactant, same amount of magnesium, you will produce the same amount of products. But the ethanolic acid ion will the ethanolic acid will take more time because of this constantly produce some H3O plus, then collide with the magnesium, then gets used up, then shift to the right to make more H3O plus, which then react with the magnesium, and that cycle just continues to happen until there's no more, one of the reactants has run out, there's no more reaction after that. Okay, but that's really a lot extra stuff, but you know, That's what you're here for, you know, just in case this sort of thing is being asked. But here we go, because you got HNO3 completely dissociate, it has a high concentration of that, and therefore you have a high rate of reaction, because the more ions available at the beginning per unit volume, there will be more effective collision per unit time or per second. Okay, so that's the end of this 2.6 examination paper, and I have done every single topic for level 2 chem, covered all the exams in 2019 of 2019 and 2018. So that's, I believe that's enough. And so good luck with your study, and I'll see you guys next time. Bye bye.